Hello, my name is Michael Banner from Mikro, Germany. I would like to talk about safe communication interfaces in the aerospace market. So what is safe communication in aerospace? At the moment it's quite simple. You see a lot of systems. You see all the airplanes with really low functionality. So if you look in the 70s, very limited, 10, 20, really important electronic systems. If you look in the 90s, you have the A320 in the range of 60 important electronic interfaces. And if you look in the 2008, you will find the A380 with a range of 100 important electronic systems in that airplane. If you look on the functionality inside an airplane, it's much more increasing. So you have about 1,000 times higher, or 10,000 times higher functionality in an A380 compared to an old airplane. So the demand for new interfaces, new bandwidths are increasing. So what are the old interfaces in an airplane? ARINC 429. It's still available, it's still used, it's still important, but it's very limited. So you have only one transmitter and you have up to 20 receivers in such a system. And you need a point-to-point communication for each interface. So if you want to have a communication from person A to person B, you need a dedicated line. If you need additional communication from A to C, you need also additional line. That means you need a huge number of cables. It's a lot of weight, and so it's not so nice to have it. Also, maintenance is not so easy if you have a lot of cables. So the second standard, which is still available, is the middle standard 1553. It's much better. It's already a bus system. So you have a bus controller, which is controlling the bus, and you have up to 31 interfaces on that bus. So communication is much easier to do, but it's still limited. So if you look on the performance side, ARINC 429 is quite low. The maximum speed you're talking about 100 kilobits per second. So it's not up to now to have this nice performance. Middle standard is also limited. You're talking about 1 megabit. You just heard about cloud, 10 gigabits. So 1 megabit and 10 gigabits, no, it's not the right performance. So what's next? I think that's the next question. What is the next interface for an airplane? I called it next generation. I think many of you knowing about that. But if you're talking about next generation, you need more performance. More performance in that area is 1,000 times higher performance compared to the ARINC 429. It's still a good increase here. So Jerry, what do you think? What is the basic architecture for a next generation communication interface? Fiber. Yeah, you're close. It's still copper. It's not fiber, but it's based on IEEE Ethernet. So it's much better. You know it from every IT department, but it's already limited for that architecture. So we have to extend it with additional functionality. So you need redundancy for that. You need a good available system. It's really small. You need a deterministic behavior. That means you have to know in a safe system in which time you can transmit your data. So it's not allowed to have an uncontrollable jitter like in normal Ethernet. So you have to do measures for that. Also, you have to have exactly your bandwidth you needed. So you have to guarantee your bandwidth in such a system. You have to have a safe system. Because communication in an airplane where you directly control an airplane with simply some cables, you need safety. Okay. So how does a modern IFTX system look like? It looks like a normal Ethernet architecture. So you have one transmitter, you have an Ethernet switch, and you have some receivers, like you know it from your IT department at home. But with additional functionality like the redundancy, you have a much more reliable system. You have availability much higher. For that, you need independent interfaces on each endpoint. But it's quite simple and it's already inside the standard. So you have 2 transmitters and receivers on each interface, and you need only 1 additional switch to have a real redundant system and much higher availability for such a system. What you also would like to do is to mix different design assurance levels inside the system. So you have real important systems where you have direct control about your airplane. So it's a DAL-A system. It's highly safety reliable, and it's really important to have safe communication. But you need also information maybe for a ventilation system, which is not safety relevant. But you have to bring all that information together. So you have to have a system where you can mix different design assurance levels. And sometimes you need also direct communication between system A and system B. All that can be done with virtual links. So it's quite a good way to save also bandwidth, because you have more or less a point-to-point communications inside the Ethernet architecture. To show you a little bit about the modern architecture in an airplane, I have a picture for you from an A380. So the red boxes in the middle are Ethernet switches. So you have in total 9 Ethernet switches, which are done in a redundant way. You have also the flight system, which is more or less safety critical. You have the cockpit, which is also safety critical. And you have the passenger area, which is not safety critical in normal. All the things are directly connected together, so you have a really limited number of cables. You have still a lot of cables, but compared to all interfaces, the number is extremely reduced, and so the weight of the airplane is dramatically reduced. In sum, you have about 20 connections to each Ethernet switch, and you have in total about 80 systems which are connected to that meshed area network. So in current architectures, like you have seen in the A380, the main interfaces are flight computers. So it's still limited because AFDX is huge at the moment. It's not so good to scale down at the moment, but at the moment you see also some thoughts to bring it down to smaller system. I think you also can imagine that if you use a PMC module, like you can see it, it's quite huge. If you want to bring it to an endpoint, to a small endpoint, it's too big. So you have to find better solutions. I call them midterm solutions. We see a lot of requests at the moment from different companies, and they would like to bring AFDX to a really endpoint. So they would like to directly control each flap by AFDX. In the current airplane, you have a flight computer, or a small computing box, which is controlling all the flaps. But you have also a lot of cables from that box to each flap, and you have a limited control of that. Their idea is to bring a small controller to each flap, for example. But for that, you need a small solution, you need a cheap solution, and you need gateway solutions. Because some of the older flaps, which are already installed, can only communicate via CAN or with digital I/O. So you're limited. And so you have to find solutions for gateways. But it's quite possible, and it's also possible to shrink it down from the functionality side. So you can build small single-chip solutions instead of big PMC modules. So you have a good chance to bring it down to smaller systems directly to the endpoint. Also, some companies have the idea to bring AFDX directly to a small display. At the moment, you have one big computer, but it's still limited because you need a lot of cables to communicate communicate to each display. If you have only an Ethernet cable or AFDX cable, so it's quite easy to install it. What is the long-term solutions? I call it Internet of Things for an airplane. I think that will come next. With tiny, small, single-chip solutions, with small gateways, you can also bring that functionality really to the passengers. Sometimes you need some information as a passenger also. You would like to see the height of the flying height of an airplane. Yes, you have it already. But sometimes it's much better to know about where you exactly are, or informations like the weather, or so on. So it's much better. You have direct communication from the flight system to the passenger. I think that will be the next step. I hope it's the next step, but all of them, of our industry, have to do it to bring systems tight, to reduce the functionality, but all that can be easily done with FPGA designs. I think that is the biggest benefit if you come from a pure ASIC design, bring it down to a small FPGA, and so you can easily adapt to the customer demands, like gateways, like I/O, directly communicated via AFDX. So why we need all of that? I think the major things why we need it, we need more safety inside an airplane. I think we are on a good track, but safety cannot be top. So you have every time potential to be better. Typically, the customers and the passengers inside an airplane are requesting more and more functionality. They would like to have more comfort. And so also you see a lot of requests from the end customer side. Also, I was talking about the weight. If you have a lot of cables, you have a lot of weight. But you would like to increase the number of passengers in an airplane. Or you would like to reduce the fuel. So you have to bring down the weight of an airplane. And you need measures for that. Also, the big topic is the maintenance. So if you look on an older airplane, you have thousands of cable. And so it's really hard to find out which cable is broken. If you can reduce the number of cables, it's much easier to reduce the maintenance costs. And so it's much better for every passenger if you can bring down the costs. Next point is pricing. So if you would like to have more functionality, you have to have competitive pricing. And so you have also to do some measures to bring high-end technology like an AFDX at the moment to a better pricing, to bring it more to an endpoint device. And the basic idea is to bring much more performance into an airplane.